Mhm.
Hello, everybody. Welcome to the Space Jams podcast. I am your handsome host, Jim Murphy, and today we have a very special guest. He is a grad student at Caltech working in astronomy, time domain astronomy to be exact, looking at radio transients. Dillon, thanks for coming here today. Dillon, I got a question for you. What are you doing tonight?
So tonight I'm going to be using one of the largest telescopes in the world. I'm going to be using Keck, which is a 10-meter telescope on Mauna Kea in Hawaii. And we'll be observing basically the locations of lots of radio transients that have recently been discovered in the VLA Sky Survey, which I'm sure we'll be talking about later. And what I'm looking for, it's different depending on the kind of transient. So transient is like generically some kind of explosion or like some sort of appearing source that creates some sort of radio emission in the sky somewhere. And what I'm looking for is trying to understand what's the cause of that emission. Right? And you can characterize that based on the environment surrounding where that emission is coming from. If there's lots of like massive stars being formed around where that emission is coming from, you might think maybe it's the explosion of a star. Right? Or if it's coming from the center of a galaxy, you might think maybe it's a flare from a supermassive black hole. And if it's coming from a star, then it might just be a flare from that star itself. So we'll see. We'll see what we find tonight.
So we got different emissions and things. Is that the transient part? Is that the time domain astronomy? The thing with me, like I've tried to do a little bit of research on time domain astronomy, and I'm a historian, not a scientist. But what is time domain astronomy? Is it just what you're talking about, looking at the different emissions, or is it something else?
Yeah, so I like to think of time domain astronomy as extending astronomy into the fourth dimension. And what I mean by that is, so if you just look up at the sky, you can see, hey, there's a bunch of stars out there, right? And you can characterize those stars by like their position in the sky, kind of, what angle they make this way and what angle they make that way, right? I know you can't see it if you're listening to the audio podcast, but just think of it as like left and right, right? And up and down. So that's the two directions. It's a two-dimensional astronomy. And that's probably what like the ancient Greeks thought of when it came to astronomy. But then through various techniques, you can also extend it into the third dimension. And that's something that's been really developed in the past 100 years or so. And you can start measuring how far away something is. Right? The universe is a three-dimensional space. But then there's also a fourth dimension, which is time. And those stars and those galaxies and everything else that's out there, they're not just fixed. They're always changing. They're always getting brighter and dimmer. They're moving, all sorts of stuff, right? And so what I'm trying to do is understand specifically how the radio sky changes with time. And not just like, on billions of years of time scales. Right? I'm not talking about like the universe expanding and things like that. I'm talking more about like a star exploding in a supernova and ejecting its guts out into the universe, and those guts slam into gas that was released by the star before it died in the form of winds or in the form of sometimes eruptions. And when those guts slam into the gas that's out there, it creates what's called a shock. And that shock, think of a shock like a traffic jam, right? Like you're driving 100 miles an hour on the freeway. Actually, no, you're driving 70 miles an hour on the freeway because you're a good law-abiding citizen. And all of a sudden, you see a bunch of like cars slamming on the brakes in front of you, and you got to slam on your brake too, right? Except the stuff that's being ejected from the star can't slam on the brakes, right? It's not like a conscious human being with with a foot on the gas pedal and the brakes, right? It just crashes straight into the slow gas that was in front of it, right? And when it crashes into that, that accelerates lots of really fast charged particles, and that's what creates the emission that I'm looking at. That's like one way to produce it.
All right.
Just to give you a flavor of what's happening.
So you're kind of looking at the ends of stars. is what it seems like, and like those types of things. That's super interesting. Is it only stars, or I'm not sure if this is completely right, but there's like pulsars and black holes. Like, can time domain astronomy help find those as well, or is it kind of like a black hole? A black hole is black, and maybe the explosion of a star helps reveal it, like from the distance or something like that. How does that work, or is it just stars?
Yeah, no, there's tons of different things that can produce explosions that appear in the radio, and one of them is stars that are blowing up, like I was just saying. But another one is black holes flaring, and what that means is you think of a black hole as something that's just black. You look at it and you can't see it, right? But there actually is emission coming from black holes, not from the black holes themselves, but from the material that's constantly falling into the black hole. So think of like dropping, a weight, like a 10-ton weight from like the upper atmosphere or something, right? Like when it hits the ground, it's going to release a lot of energy. And that's because it fell a really long way. It went from a lot of gravitational potential energy high up, and it converted that into, heat, into sound, into like just brute force, like kinetic energy when it hit the ground. And that's the same thing when something falls into a black hole, except much, much more energetic. Because the black hole is tiny and it's extremely massive. And those two factors basically mean that you're releasing a huge amount of energy when even a small particle of gas comes in. And astronomers think of this kind of in terms of the thing's rest mass energy. So, Einstein's equation, E equals mc squared, right?
Yes, I mean, I know it so well.
I mean, I'm sure you heard of the equation, even if you don't know exactly what it means, right?
I practically wrote it, Dylan. I practically wrote it.
Yeah. So what it means is that the energy that's stored in every atom and every little bit of mass. So the mass is m, right? The energy is E. There's a ton of energy stored in every little bit of mass, and you can get the amount of energy by multiplying the mass by the speed of light squared. And as I'm sure you know, the speed of light is huge, right? Light travels around the Earth like 8 times a second or something like that. So you can actually release like 10 to 40% of the rest mass energy, the mc squared energy of a piece of matter just by flinging it into a black hole. And to give you a sense of just how amazing that is, I actually don't have these numbers exactly in my head, but nuclear fusion, for example, like in the core of the sun, or maybe in a fusion reactor, releases like 0.1% or something like that, as opposed to like 10 to 40%. And then like every other source of generation, like burning gasoline or something, is like, orders of magnitude, like hundreds, thousands of times less efficient than that. And so black holes are like the most efficient engines in the universe. And there's constantly matter that's falling into them. And so that energy has to go somewhere. Some of it goes into the black hole itself. That's not the 10 to 40% that you see. Right? The 10 to 40% that you see is actually stuff that's radiated away in terms of light and in terms of, other kinds of energy. So black holes are actually some of the brightest things in the radio sky. It turns out that there is a lot of radio emission that gets produced by black holes, not directly by the infall, but because for some reason that astronomers don't really understand, black holes tend to eject, when things fall in, they tend to eject jets. And these jets are like close to the speed of light, and they're just coming out of the black hole in two opposite directions. And there's all sorts of weird behaviors of those jets that can cause them to change in time. And also they have lots of effects on the galaxies that host them. Like they can blow out a lot of the gas that's in the nucleus of the galaxy, and then they can potentially stop stars from forming nearby. There's all sorts of cool stuff that we could get into if you want.
Yeah, that's awesome. I really like the idea of thinking of the black hole as the most efficient engine in the universe, where like immediately my mind thought of like the combustion engine and how that was like revolutionary. But the combustion engine is very it wastes a lot of energy with like heat and sound and everything. It wastes a lot of energy, so it's not that great. And that's why, while among other things, it's better for the earth and whatever. But electric engines can like they can regain fuel or battery power from like braking, so like they can take that energy back. Like those are really interesting things, and it makes me think in kind of a science fiction kind of way. If black holes are the engines of the universe, like what are they powering? Like what are they doing? So that's like super cool. Any speculation? I mean, we have the captain, as we said, we have Jean-Luc right with us, telling us he's about to do a sonnet from Shakespeare. But what are the engines for? Like any speculation? Tell me, Dylan. Tell me.
Yeah, I don't know if they're for anything, but I have read at some point, I might be getting this wrong, but I have read at some point like science fiction speculation that some extremely advanced civilizations, maybe us in like a million years time, will be mining black holes for energy, right? Like you throw particles of mass into that black hole, never to be seen again, and that mass generates tons and tons of heat and light and jets and whatnot. And if you can somehow harness that energy and divert it into the purpose that you want, right, then you can you can use the most efficient energy engines in the universe. But like when you're talking about internal combustion engines and how like the heat and the sound are wasted, right? They're only wasted because they're not doing the thing that humans want, right? That's kind of what black holes are doing too, right? You're throwing mass, or mass is falling into them, and they're not necessarily doing the things that humans want. But if you can find a way to make that thing do the thing that you want, then that's engineering, and that's your science fiction right there.
I think it's interesting you say that because one, what a great spin on it. It's not the thing humans want, but humans did make black holes as far as we know. But human did make the engine, and it's imperfect. It doesn't work super well, and we made it. So I guess we're getting closer to making things that are perfect. But then it's like, who made black holes? What made black holes? I think they must have a purpose. It seems like if they're the way you describe them, but I think that's super cool. Um, but you have so you're doing your research tonight. You're going to be up all night. We just kind of talked about how like every minute or every second of using this telescope is like what, $1, like to use
Yeah,
it. That's crazy.
yeah, yeah. It's not that I'm paying this cost, or that my advisor is paying this cost or anything like that, right? It's like the total amortized cost of like building the telescope and running it and everything, right? But it sort of just gives you a sense of like how much investment people have put into into making these telescopes, right? And how like you kind of have to think carefully about everything that you're doing. You can't really afford to waste time.
Yeah, time is money. So
Mhm.
I think you also said they're like the second largest radio telescopes in the world?
Oh, so these are optical telescopes, the one that I'm
I'm sorry.
using tonight.
Gotcha.
Um, but yeah, they're some of the largest optical telescopes in the world. Optical telescopes are really measured by like the diameter of their main mirrors, their primary mirrors.
Gotcha.
And the biggest ones in the world so far are sort of 10-meter class telescopes. And there's a few of them around the world, but these are some of the 10 meters.
That's pretty cool. And since like you're radio, a lot of radio astronomy and things like that, and you must have heard that the Arecibo radio telescope like was finally like crashed on itself, and there was like that whole big debacle, and it's a kind of sad. Do
Yeah.
you have any like thoughts about that? Like, were you ever going to be able to like use that, or have you ever used anything from that?
I mean, it is really sad, right? Because I've never actually been to Arecibo, but I've always wanted to go see it. Uh, and a lot of my friends actually have been there. Like they have pictures, like they posted on Facebook of like pictures of themselves at the telescope, right? And they either used the telescope or they're visiting there. Uh, and yeah, it's definitely a loss. It's a little bit softened by the fact that there is sort of like a bigger Arecibo now that has been built. It's located in China. It's
Yeah, I
called
heard about that.
yeah. But there's all sorts of like, geopolitical reasons why, US scientists might not like have the most straightforward path to using fast. I don't actually know too much about that, but you know, there's definitely like a little bit of concern that that like we'll be losing, at least US astronomy will be losing a lot of the same capabilities.
I heard that they were thinking about replacing Arecibo. I'm not sure how much funding that would get, but what is the, obviously a bigger mirror in a telescope, the wider, scope you have, which is great. Hubble has been up there forever. It's like the biggest telescope we have in outer space, but now they're putting up the James Webb telescope, which is going to go up at some point this year. I don't know if you like have any knowledge about that or anything, but I'm excited for that to go up. And I'm not really certain, like it has all these like hexagonal panels. I think that's pretty cool, but I think it's a lot bigger than Hubble. Like the mirror base that it has is a lot bigger. But what is the advantage of having Arecibo? Why does it have to be so big? Like why was that an advantage? Like I think it might be obvious, but I have no idea.
Mm-hmm. Yeah, so there are a couple of reasons why you want your telescopes to be big, right? And actually, just for scale, Arecibo I think was like 300 meters in diameter. Think of it as like 3 football fields just back to back, like across the thing. And fast is actually 500 meters, so it's 5 football fields.
Wow.
And that so Arecibo is a radio telescope, right? And that's the only reason why you can construct it to be so big. The optical telescope that I'm using tonight is 10 meters. It's a tenth of a football field across, right? But that's because the optical telescope has to be made out of glass, the mirror does. Whereas the radio mirror, quote unquote mirror, is really made out of like concrete and things like that. Just because radio waves are so long, they bounce off of concrete as well. Right? Actually, it's not concrete. I actually don't know what it's made out of. Maybe some sort of metal.
That's really interesting.
Yeah, something that's not like, it doesn't have to be as smooth and polished as an optical mirror.
Interesting.
But you asked earlier why you want to have large telescopes, and there's two main reasons. One is resolution, so like how fine the detail you can see using your telescopes. The resolution of a telescope is fundamentally limited by what's called the diffraction limit. If you take something like a source of light that's infinitely small, like you could always get more and more detail by having better and better resolution, and you shine it at your telescope, then it's going to be spread by the physics of diffraction into a source on your detector. So like your camera's CCD, or your photographic plate, or whatever, your film, right? It's going to be spread into something that's of size the wavelength of the light divided by the diameter of your telescope. The wavelength of your light, you can't change that. That's the wavelength that you're trying to look at. But the diameter of your telescope, if you make that bigger, then the amount it's spread by gets smaller. So that's one reason why you want to build bigger telescopes. And the other reason you want to build big telescopes, and that actually is the real reason why Arecibo was so important, is because of sensitivity. So if you imagine your telescope as like a bucket, and you imagine light from the universe coming down as like rain, right? If you want to catch lots and lots of rain, you want to have a big bucket, right? Because if your bucket's the size of my teacup, then you're only catching a little bit. And if the rain from your source is very sparse, if like one drop is falling every 10 minutes, then you better have a big bucket, otherwise you're never going to catch any drops, right? But yeah, so that's really the reason why. Right?
All right, nice. Yeah. Sweet. Yeah, I figured that bigger, more information better, but it's an interesting to figure out why, especially because the resolution, and you talk about how fine, usually you think fine, it's like small, delicate, but you can make something big get very fine. I like that. It's cool. So I guess, well, we're on the subject of like new, radio telescopes and things like that, telescopes. What is the next step for astronomy and radio astronomy? Like the Arecibo just fell. That's kind of a big thing. But there's a bigger one in China now. So what's the next step? Why is there, I guess there's the reason there's no radio telescopes. I was about to say no telescope in space, but I don't think that's true. I don't know. What's the next step for radio astronomy?
Yeah. So personally, I think that radio astronomy is actually going through a bit of a revolution right now. And it's not a hardware revolution, it's a software revolution. So what I mean by that is, remember when we were talking about just now about how you get fine detail by making your telescopes bigger?
Mm-hmm.
There's another way to get fine detail, and that is by having two telescopes that are separated from each other. So the telescope that I primarily use is called the Very Large Array. It's actually not one dish, it's 27 dishes. And they're arranged in like a Y formation, and they're out in like the middle of the New Mexico desert. Mm-hmm. But those dishes actually sit on rails, right? There's a Y-shaped rail, and there's like, several ton rail carts that actually are able to move these dishes to different configurations. You can move them farther away from each other, you can move them closer to each other. And it turns out that if you measure the signal in all 27 of these telescopes, or even in just two telescopes that are separated from each other, you can actually synthesize an image. You can use software magic to recover detail that is on the scale of the wavelength of light divided by the separation of those two telescopes. So instead of building a telescope that is 300 meters in diameter, or like a kilometer in diameter, or hundreds of or thousands of kilometers in diameter, you can just separate two telescopes by that distance, and you can get the same resolution. Huh. Now you might think that sounds too good to be true, right? Why would anybody build giant telescopes if that were the case? And that comes down to the second thing. It comes down to the second thing and something else. The second thing that we were talking about earlier is having a big bucket, right? And if you have two small telescopes that are just separated by a large distance, you still only have two small teacups that you're trying to collect the rain with. And if you don't see anything, then oh well, right? But you can get around that by having not just two, you can get around that by having 27, like the Very Large Array. Or in the case of some of these arrays that are being built nowadays or being proposed, you can get around that by having hundreds, maybe even thousands of these antennas, right? And it turns out that it's actually cheaper to produce like thousands of like 1 or 2 meter antennas than it is to create one giant telescope that has the same area as those thousands combined, right? For engineering reasons. And so that, I think, is really the future of radio astronomy, is more telescopes separated by large distances, and the corresponding software magic that I sort of glazed over that makes them work, right? And that software magic actually, you need supercomputers to be able to crunch the data from all of these combinations of telescopes, because you need to get one piece of data for every pair of telescopes, right? If you have a single dish, then you get one piece of data. If you have two dishes, you get two pieces of data. Or actually, no, you get one piece of data because it's one pair. But if you have three, then you have to look at the first one and the second one, the second and the third, and the third and the first. If you have four, then you have to do 1 and 2, 2 and 3, 1 and 2, 1 and 3, 2 and 3. You get the picture, right?
Yeah.
It grows as like the square of the number of telescopes you have. And you can imagine if you have 1,000 of them, then that's a lot of computation that you have to do.
That's exhausting. Sounds exhausting. Yeah. I guess that's why I'm not an astronomer.
Well, that's why you're not a computer, right? We outsource that hard work to dedicated supercomputers that all they do is crunch numbers all day.
Yeah. So you're doing some research tonight, and you've been doing your research and everything. What do you hope to accomplish with your research in particular? So like your mission.
Yeah, so this really gets back to what I was talking about earlier about extending radio astronomy into the fourth dimension. Right? I'm not the only person, of course, that worked on this, but one of the things that I've personally contributed is a lot of analysis for this one particular survey that's being done with the VLA called the VLA Sky Survey. And what the VLA Sky Survey is those 27 dishes in the New Mexico desert, they're observing the entire sky 3 times over the course of 7 years. And over the course of those observations, they're going to detect like millions of sources, and they're going to detect them, or like 2 million or so, and they're going to detect them 3 times. And some of those sources a lot of those sources actually will change in brightness. Some of those sources will be present in one observation, but not present in a previous observation, or maybe in an observation after that. Right? And what I'm doing is I'm looking for all these things. I'm looking for the sources that are changing brightness. I'm looking for the sources that are appearing and disappearing in the sky. And I'm using techniques from not just radio astronomy, but optical astronomy and infrared astronomy to try and understand what's causing those sources to appear and disappear. Right? And of course, I'm using understanding that has been gained from like the previous century of astronomy and like the theoretical astrophysics and all that stuff to try and model these things as well.
Mm. So that's, that I think it's super cool. And it's so hard for a lot of people, including myself, I think, to understand like what scientists and astronomers and anyone in this field do, because one, it takes so long to do these things. Like there are people's missions who go to different planets and they take years, and you might start it when you're 20 and it'll end when you're 50. So it takes a lot of time to get used to it. And some things that people do are they like, oh, I did this thing and it looks small, but it's so important. And I think that's interesting. So like how long will it take for you to get the answers you're looking for from, like, is it immediate or is it going to take some time? Or
Oh, I mean, it totally depends on what you mean by the answers that I'm looking for, right?
oh
If the answer that I'm looking for is, hey, I took an observation of this thing and I want to know exactly how bright it is at 3 gigahertz, then the answer might be like a couple hours a day, something like that, right? But if the answer that you're looking for is, okay, it changed by, this amount and in this way, why? Then the answer might take a much longer time, right? So, for example, like astronomers and other scientists report their results by writing papers about them, by writing scientific papers that you submit to journals, right? And some papers, they're kind of quick, and like kind of quick, I mean like they take a couple of months to write. But some papers, they take years to write. Right? And I just submitted a paper actually that I've been working on since I discovered the source in like 2017, I think. Yeah.
wow.
Yeah.
That is some paper, I'm sure. Jeez.
It's taken us a long time to understand like what the source is, and we think we finally found the answer, but we're not. But we'll see. Yeah.
That's cool. No, that's cool. So, you say you work on a team, like you don't do anything alone really. Like how did you are there any like professions in you, or are there any professionals in the world of astronomy that like you look up to, or like anyone you, or like, look as an example of like what you want to be or what you want to be like or something?
Tons of people. Yeah. I mean, I don't think there's any one person who I want to become the clone of, right? Like I am my own person, but I like to think that everybody I meet, I learn something from, right? And that includes my advisor, for example. I work with a professor named Greg Hallinan, and Greg's like talent in my eyes, like the one thing that really makes him stand out well, there's several things, but the one thing that really has made an impression on me is his imagination and his creativity. Right? Uh, like he'll look at a problem and he'll think, hey, it could be like, these 15 different like sort of crazy sounding things, right? And 14 of them will be wrong, but one of them might be right, right? And it's kind of my job to sort of go down these rabbit holes and go, Greg, you're crazy on like those 14, but then go, you might be right on the 15th. Uh, and that's actually what happened with this paper that took like many years to write. Right? Greg just threw like so many ideas at me, and I was like, no, it can't be that, can't be that, can't be that. But then finally we settled on something that we thought, oh, yeah, could be. And it turned out to be interpretation.
That's awesome. I mean, it sounds like you should be on the Enterprise right now, solving problems, going places with good old Jean-Luc right there. That's really cool.
Would be cool.
Yeah. Of being creative and like coming up with ideas, even though, and then figuring out that's wrong, and then out of a bunch of different options, and one is like, wait a minute, that's very cool. I feel like people are afraid to think of ideas like a paperclip is a paperclip, but they don't want to make a paperclip out of like sponge, or they don't want to make it 50 feet tall. Like, how big or what is a paperclip? Like, it could be anything. It could be made of anything. People are afraid to like think that way. I think that's like something that's super important, and innovative people bring that to the table. So I think an important question to ask is how did you get into time domain astronomy? How'd you get into astronomy? How'd you make your way to Caltech? How did it happen?
Completely randomly. I mean, we were talking earlier about how a lot of astronomers have stories like, oh, I like grew up in like a really rural place, and like I looked up at the stars and they were all so beautiful every night. I just like fell asleep in the field looking up, right? And that actually was kind of like my advisor. My advisor grew up in sort of rural Ireland, right? And he had like the most gorgeous view of the stars every single night.
That's
awesome. But I grew up in the middle of San Francisco, and I could see like the Big Dipper, and that was about it.
But still,
yeah, it's still cool, but didn't really get to experience the whole night sky thing. And so my first exposure to astronomy really was on a whim. I decided to go to this astronomy camp that was run by this program that was like affiliated with Duke University. And they're out in this place in the middle of the Pisgah National Forest in North Carolina, at this like Cold War era observatory that was probably used for like tracking like Soviet satellites or something like that.
Nice.
And now it's called Perry, the Pisgah Astronomical Radio. I can't remember what the I stands for. But anyways, there's like an educational program that's being run out there now. And we just got to go out there and like operate these giant radio telescopes, as well as like a couple of optical telescopes that were out there if you wanted to. And that was actually the first time that I really got to see the dark night sky. And I remember actually sometime at like 2 a.m. where I just like went outside and looked up, and I just like laid there literally in the middle of the road. Like, thankfully there weren't any cars driving by. And I just like looked up at the stars for like a straight hour from like 2 to 3 a.m. And I was like, wow, this is really cool. So that was my first exposure, but that's not really what like got me into like doing astronomy as a job. Right? What got me into doing astronomy as a job was I took this intro class from this wonderful professor named Phil Choi at Pomona College, where I went. And there I got to learn about like the actual astrophysics, the actual like reason why like stars shine and why galaxies are the way they are and why stars blow up and all that stuff. Of course, at like a really introductory level. But if you ever get a chance, like if you're in college, then I would highly recommend just taking one of those intro astronomy classes. They're just really, really fun. And I loved it. I loved it so much that the professor noticed, Phil noticed, and he was like, hey, Dillon, like you should go apply for this summer internship doing astronomy research. And, and I was like, yeah, I need a summer job. Why not? And so I did, and kind of just snowballed from there. I started working on radio observations of star forming regions in nearby galaxies. And then from there, I worked a lot on like radio observations of galaxies. And when I came to Caltech, Greg emailed me and he was like, hey, I've got this project that might be really interesting to you, looking for radio transients. And I was like, what's a radio transient? And he was like, don't worry, like I'll teach you everything you need to know. And he sent me like a PBS documentary on gamma ray bursts or something like that. And uh, and he told me, when I'm like hopping into a new field, which Greg does all the time, like he works on like 10 different fields. He's like, I start from just Googling something, and then I look at Wikipedia, and then like, if I really need to, I'll go read the papers, right? And then I'll dig into it myself. And that's kind of what I've embraced since. It's you start from the really basics, and sometimes you just stumble into something that's really cool, and you ramp up from there.
That's cool. Actually, I was reading last night this little thing, like Ralph Waldo Emerson, he was talking about, like, if you do this one thing and then you go out and try to do it and you fail, and you'll be a failure your whole life. But if you try a bunch of different things and you learn about a bunch of different things, you'll always succeed, because you're just going to keep trying. It'll keep becoming you'll keep being interested all the time. It'll be it's like a fun way to live. And I think that's pretty cool. So now here's the other important question. So how did you get into it? That's great. First of all, it sounded like you had a really sappy story of laying up, in the middle of nowhere on the road. Yeah. Okay. So I wasn't interested when I was a kid. Well, okay. You laid on the asphalt for an hour looking at the stars. Liar. But the other question is, why should people care about time domain astronomy?
Honestly, because it's fun, right? I think of astronomy as like is kind of being similar to math and art, and to some things that like are not as practical, and don't have like as much direct relevance to our lives, but they're just fun, right? And like, can you imagine a world without like art or music or anything like that, right?
Well, you said math.
Yeah, like math too. I think of math that way too.
You think math
not
is
like
fun?
Yeah, I think math is fun. Some kinds of math, not the kind of math you learn in school. I hated math. Like I was good at math, and like I didn't like hate it, but I hated math class when I was in high school. Right? And it's because they just make you do all these like drills, and they make you like solve your quadratic equations and all that crap, right? And like you don't see the beauty behind it. But when you go to college and you like take a couple of advanced math classes, you get to learn cool things like group theory and graph theory and stuff like that. And it's just like, hey, let's find all the really deep and like hidden patterns within within these structures that humans have invented, that hey, for some reason they also are extremely applicable to like everywhere in life, right? And like nobody really understands why math, that like the system of numbers and like symbols and everything that humans invented actually corresponds to nature so well, but it does, right? So that's one reason why people study math, but that's not really the reason why I studied math. The reason why I studied math is because I thought it was beautiful. Right? And so that's kind of like the reason why I study astronomy too. Like I could be making probably like 10 times what I make right now as a grad student, right? Working like at Google or something like that. But I choose not to, because I'm just having more fun like studying space. Right?
God, you Dylan.
Yeah. And at some point, I might stop having fun, because academia is definitely not like a cakewalk, and there's lots of stressful aspects of it. There's lots of like, not so fun things about it. Uh, and at some point I might like stop doing astronomy and I might just go take an industry job. And to me, it's like, what am I having fun with right now? And what do I think I'll have fun with, like looking 10 years in the future, right? And I'll make my decision on what I do in my life based on that.
Hey, look, 15 decisions, some of them could be right, some of them could be wrong. It's the same. It's awesome.
True. Yeah.
That's very cool. I always like to ask them, like the people, why it's important, because I find that when a lot of people ask that question to people about space, they're like, well, why should I care? Like, why is this important? Like, there's so much stuff going on here. And like, I think, when it comes to human or any type of space exploration, it's simply like, it can just be beautiful. That can just be the reason, and like thought provoking and things like that. So that's awesome. But a lot of things like, so, I always think of what's the most important aspect of space exploration and stuff like that. Like, do you have an opinion of what you think the most important aspect of space exploration is?
Yeah, so I mean, it depends on what you mean by important, right? I mean, there's important in the sense that like it's beautiful, which is what motivates me, right? But there's also important in the sense that it might be good for humanity. Right? And there are like lots of resources in space that we could be using. There's lots of expansion of like human civilization that science fiction authors have really explored that I don't know all that much about, but there's a lot of potential out in space. Right? Space, like it's the final frontier, and so
Yes.
yeah. So that's also like a reason why you might want to explore space.
Yeah, cool. So you talked a little about there's like a lot of possibility in space. We have some, I mean, we're living in the commercial space age, with the launching of the Demo 2 last summer, SpaceX's Demo 2 and everything. How do you feel about the commercial space age? Or, or how do you feel about civilian astronauts? Like, we're going to have the first all civilian crewed astronaut crew going up soon too on SpaceX. Are these things exciting?
Yeah. I think it's cool stuff. It's very pioneering work. There is always like a tension, right? Whenever something changes really quickly, you start like worrying about, are you stepping on people? Are you like disadvantaging them in some way? But also, there's the flip side of that, which is like what humanity is gaining from it, right? And it's always like a complicated balance that, like, I don't really like it's not really what I study. Like I'm not, an engineer who works at SpaceX, and I'm also not like an ethicist who like thinks about the like implications of all these things, right? But it's definitely like an interesting dynamic that plays out. Uh, yeah, and if you ask me like, more of a specific question, then maybe I'll have something, but I haven't spent too much time thinking about it myself. So,
All right. Well, how about colonizing the moon and Mars?
colonizing the moon and Mars. I think that it's probably a good thing overall to like establish human bases on the moon and Mars. Uh, whether like it's cost effective and what exactly we can get out of it compared to like what problems we can fix on Earth using that money, I don't know. But it's also like one of those highly speculative things that like can really grow in the future, right? And it's probably worth it. Is my guesstimate.
Yeah.
Yeah.
All right. Yeah. Last week there was DARPA was looking for like they was surveying the private sector for capabilities of building a factory on the moon, and I thought that was really cool because I don't even like to think about structures like with a purpose other than, I mean, it's kind of other than scientific, which I think is cool because other than scientific means that, people, it has a function that can help like other people, like jobs and creation. Those things are cool. But I thought that was like a really cool step that people are starting to think about that. But yeah, I agree. I like how you take everything. I've found this with a lot of people, a lot of smart people I talk to. You ask them a question and you expect an ordinary answer, and then they give you something that you weren't even expecting at all. And I think that's hilarious. They'll be like, well, it depends on what you think about important, or like what, there's the two sides to the thing, to the question that you're actually asking. It's awesome. It's great. Another one, which I think is kind of a fun question. Actually, we're pretty much down to the fun questions at this point, so you can breathe. It's just opinions now. Don't worry about it. But so if you could go to one place, moon, planet, star, black hole, you'd live. If it was a black hole or a star, you'd be fine. Which one would you do?
Probably like if there were a planet that were habitable, and there were like life forms on it, I would love to see that. Right? Like if you were to go to a moon, I mean, moons could be habitable places, right?
Yeah.
There could be moons with atmospheres and like life forms on it and everything. But stars, like if you were to sit on a star, even if you didn't get immediately burned up, you would just see a field of fire as far as you could see, right? And you would like immediately get blinded. And even if you didn't get blinded, all you would see is fire, right? Or like plasma. And it's like, okay, like that would be cool for like a minute, but then it would get old, right? And if you're going to a black hole, it would be really cool. Like you would see probably like the interstellar black hole, right? You would see like maybe gravitational lensing of stars behind it, but then also you would just be stuck in the middle of space and like what's out there. But if you were able to like actually walk around on a planet that where you could breathe and like there'd be really like interesting animals that were walking around, or maybe even like advanced civilizations that you can interact with, like that would be so cool.
Yeah, that would be awesome. Yeah, and you're a big nature guy. Like you have your two bunnies, and you like love going on the hikes and stuff in nature, and so I think that wasn't a surprising answer. But yeah, I think, gosh, I that's one of the things where it will be really cool when we find something like that, any kind of life, but it will also be quite shocking and maybe even frightening at the same time, which I think is basically what science is. It's cool and also frightening. But you spoke a little bit about like science fiction has looked into exploration, different types of things we can do out there. Do you have any favorite science fiction book, or any favorite book at all? Doesn't have to be science fiction.
Yeah, favorite science fiction book I think is probably the two collections of short stories written by Ted Chiang. Uh, now that I say that, like the first one is called Stories of Your Life, and I can't even remember what the second one's called. But it came out like last year or something like that. Although the stories have been out there for a while.
Yeah.
And what I really like about them is that he takes like different small ideas and just runs with them. And I suppose that's really what science fiction short story writers do. But uh, it's that like uh, just taking sort of a small seed and exploring like all the implications of that thing, of that seed, that I really like. And I don't know, I kind of like doing that in my work too, right? Like I'll get like a little bit of inspiration and then sort of like see how far I can build it coming from that little bit. And that's kind of what Ted Chiang does as well.
That's cool. Nice. Good answer. Not an answer we've had before. We've had a couple Martians. We've had a couple, trying to think, I can't remember the name of it. Oh, Hitchhiker's Guide. We've had a couple. We've had one or two.
Yeah.
The classic. Sarah Blunt talked about Lord of the Rings. I think we talked about that a little bit, which is great. I mean, that's my favorite. Got my poster up here. If I had to have another person behind me, it would probably be Aragorn or Gandalf. But yeah, it's classic stuff. You talked a little bit. You talked a little bit about a million years from now, what we might be doing. What do you think human beings will be doing in 100 years, scientifically speaking? Where are we going?
In 100 years, yeah, in 100 years, probably the biggest thing is going to be climate change and how humanity responds to that, right? Because we're going to see like the really severe effects of climate change, like when we're old, right? In sort of that sort of time scale. And hopefully we'll be able to, through some combination of like humanity cooperating and like switching to more renewable energy, and also like science just getting better at dealing with this kind of stuff. Like hopefully we'll be able to address it. But that's like the big crisis that is facing all of humanity in like the next 100 years. There's also probably lots of interesting stuff that's going to happen with energy in the next 100 years. I mean, kind of related to climate change, but like where we draw our energy from.
Black holes.
And yeah, probably not black holes in the next 100 years. Actually, I guarantee not black holes in the next 100 years, because we can't even reach like the nearest black hole in 100 years.
Nice. I like it. Throwing down the gauntlet. No way.
Yeah, I mean, like we can't even, like, because of light travel time, we can't even reach the nearest black hole, at least that we know of, in the next 100 years, right? So unless we figure out how to break the speed of light in the next 100 years, which I'm not hopeful of, nothing's happening with black holes. What else? There's lots of like understanding of human like biology and medicine, right? And that's going to be like a huge area that I'm hopeful that scientifically we'll be able to advance in the next 100 years. Like maybe we'll discover how to cure lots of diseases and hopefully prevent the next pandemic and all that stuff.
Please.
Yeah, right.
I've made it my goal to not mention basically the pandemic at all. It's really bugging me lately. It's really annoying. So yeah, gosh, let's work on that.
Yeah, I mean, if you think about it though, right? Like the previous big pandemic was 1918, the Spanish flu, right? And then like every 100 years before that, there was also another pandemic. So probably in the next 100 years, we're gonna something is gonna pop up, and hopefully we'll have the scientific tools to be able to like just stop that in its tracks before it becomes COVID-19 again.
Yeah.
Right? Worse. Yeah.
Yeah. Well, there you go. Well, that's some good stuff. So we have our final question for you, which is a doozy, coming from me, kind of a wannabe teacher, and generally interested and excited about most things space. How do we get the younger generation excited about space? Like, how do we get them interested? How do we get them to go outside and stare up at the sky, or mess around with a shuttle figure? Like, how do we do it?
That's a great question. And I really think it comes down to letting kids be kids, like letting them have their innate creativity and run with it, right? And there's a lot of components to that, right? Like a big component to that is making them like be in an environment where they feel safe in expressing that creativity. And I mean, a lot of that comes down to like, giving them like a welcoming environment, and also making sure they're like, well, taken care of at home, and like all that stuff. But also in the classroom, like as a teacher, I think it's not like cracking down on them and like forcing them to like do drills all the time, right? Like not being the sort of middle school math teachers that like I really didn't like. Like I had a math teacher in 6th grade where like I got a C in that class in 6th grade math. And the reason why was because she would give what's called homework quizzes, right? And the homework quizzes were literally, what was the answer to problem 7C on the homework? And she wouldn't tell you what problem 7C was. It was literally to see, did you do the homework? And like the homework was just incredibly boring. It was like 6x plus 2 equals 14. What's x, right? And so like I never did any of it. And so like, whenever she would give actual tests, I would get all the questions right. But like whenever she gave homework quizzes, I would get zeros. And like that balanced out to getting a C in the class. And that's exactly the kind of thing that like, kills a kid's like love of learning, right? When you try to get learning to be about like external things, like getting grades, rather than getting learning to be about like, wow, there's something cool out there, let's find out what we can learn about it. Right. And that's honestly my opinion of like how to get kids excited on anything.
Yeah, I got C's in math for a whole different reason. It's not because I knew the answer and didn't choose to do it. I came up with my own math on the spot, and it didn't pan out. I'm no Newton, so yeah.
Mm-hmm. But honestly, I mean, if like I'm sure there's something as a kid that you were just really excited about, right?
Oh
Like,
yeah.
I don't know what that is, but if you were as excited about math, like as you were about like that thing, like I'm sure you wouldn't have gotten C's in your math classes.
That's true. That's true. I guess that's why I'm a history major.
Mm-hmm. I mean, I loved history when I was in high school too. Like,
yeah.
Yeah.
I'm a history major who wants to be an astronaut. So I don't know if that pans out very well, but hopefully in the future it will.
Yeah, that's cool.
I put my lottery ticket in to be one of those civilian astronauts. So we'll see. We'll hope.
Yeah, good luck with that.
Yeah. Yeah. Good luck.
No, I mean, I didn't mean that in like a good luck with that.
Oh,
like
yeah.
That's never gonna, like
I know,
actually good.
you were sincere. Yeah, I know. It's just there's one guy. I think it's one person's gonna go up at him. I'm sure there's thousands of people, tens of thousands of people that have probably put it in. Hell, the other day you could put a letter, like a love letter, in this upcoming Virgin Galactic flight that they're doing, another test flight, and the letter would go to space, and then they would send that letter to like the person who you wanted it to go to, and it could be from space. And I did it immediately when it came out, and it bounced back. They said we have too many letters. I'm like, how is that possible? Who else is paying attention to Virgin Galactic but me? So, but yeah, so I thought that was pretty funny.
Yeah,
Dillon, it was a lot of fun. We learned a lot. So thanks so much for coming. I hope you had a good time with Jean-Luc and I.
Yeah, thanks for having me.
Yeah, I'm voting you onto the Enterprise for sure.
Appreciate that.
To check out this final frontier. All right. Well, everyone, thanks for listening. Give Dillon a round of applause. It's good stuff. Which find us on Instagram at Space Chams. It's a good time. We post things. Keeping it real. I hope everyone's having a good time out there, and everybody remember to keep looking up. Peace out, everybody.